Fellas, what's happening? It's currently 10:42, March 17th. I think there's over 130 cases of good old COVID-19 out in the wild. Looking outside, it seems to be about 78 degrees. It's cloudy, and the oak trees are still full of pollen. It's not fun. You can't tell between allergies and viruses. Anyway, this is your assignment for, I have to take a guess at it, FGAB tomorrow, second period on Wednesday, 3/18. Go ahead and review this. I'm trying to get out these next couple of slides within, it looks like 10-15 minutes. I'll do it. Let's see. Natural selection on single gene traits. If you're looking at our chart at the moment, this guy here, you're already starting to figure out what's going on. I think you guys are pretty quick there. So we're going to talk about how natural selection affects single gene traits. Let me go back and take a look at this. And those single gene traits are these guys. So it's an either or scenario. So there's no blending like we expect right here, right? So over here, obviously we have populations of brown, red, and black lizards, and clearly something's changing here. If we look over by generation 30, we can see that there's more black than brown, whereas when we started, 80% of the population was brown, 10 red, and 10 black, right? So I'll ask you a little question here, give you a couple seconds to try to answer it. What is natural selection favoring? Good, that should have taken about 2 seconds. Black is the correct answer. Why is the red one gone? It's bright red. It can be seen in the environment. Good job. So as we see that the red is gone, it can no longer reproduce. Maybe an opportunity was there for the black. Maybe the brown failed its opportunity. But this roadrunner over here was capable of catching and eating the brown ones, and the black ones by generation 30 are showing us that they are on the increase, right? So the red ones can be seen. Black lizards, as it turns out, their selective advantage just had nothing to do with camouflage. They absorb more sunlight. And what happens with ectothermic lizards, these guys, they can compete earlier into the day than the brown ones can because they absorb a little bit more sunlight. They get going sooner, and they might even have a little bit more sun energy in their body. Not that they're absorbing sun, but the heat component warms them up, so they're ready to compete. Okay, so when it's a single gene trait, one of the traits will have some sort of advantage, and one may or may not have some sort of disadvantage, right? So the bar graph, this would be 3 bar graph. It would look something on the lines of, this would be the brown population at the beginning, and that'd be red and black, and then by the time we get over here, we're going to see something of a much greater change in that bar graph. We'd only have 2 bars, right? It'd be 40-60, so we'd see 60% black and 40% brown. Okay, moving on. 3 types of natural selection on the polygenic trait. Now, polygenic, if you remember, we're back over here. That's going to be this guy. We're going to see this curve, right? And within this curve, there's an infinite number of possibilities, right? You guys know that on a curve, an infinite number of points. So there's 3 types here, and you will anticipate seeing this on, fill in the blank. Good. Test. And boy, LaFrance, close your laptop. Wait, you can't close your laptop because you need it right now. My bad. So in directional selection, the original population is this guy here, the dotted line. And we can see that there's been selection for the most extreme large-sized beak. Because what's happening is that all beak sizes, including the average beak size, have trended in this direction, right? So the whole population, I'm going to let that dissolve, go away. The whole population is now within these two lines here, and that's our new population because selection was directional and it favored the larger beaks. So what we lost was anything past this point on the line. And what we gained is anything past this point here and here. Right, so anything under here is a new phenotype, and anything over here is what was lost. So the whole population was directional for larger beaks. Could this happen in the smaller beak direction? Absolutely, right? Because as we go on to disruptive, we'll see there in a minute. In stabilizing, what does selection look like it's for? We lose the phenotypes on the outside, the extremes, and it selects for the average. So we not only do we lose diversity, we also increase the frequency of the average phenotype. So this population is going to be relatively uniform because the variance from one extreme to the next is minimal, right? So if we look back up here at directional, we can see that the frequency of the average doesn't change. All the frequencies remain the same, it's just new phenotypes. Over here, we see the frequency changes, or how common it occurs. That's called stabilizing. That's selection for the average. So in many ways, you could kind of say that this is the opposite of directional, where we're choosing for right down the middle as being the best, whereas on directional, we're going to choose on one side of the curve. Okay. And then in disruptive, this also could be considered to be the opposite of stabilizing, where instead of choosing for the average individual, the extremes are chosen for. And what's going to end up happening here is that these graphs are going to get further and further apart. And there's going to be a 0 point. I can't draw. When I draw a circle with this, you know what happens, right? It makes it doggone the window, right? Like I use sometimes. Anyhow, in disruptive, what we end up seeing is both an increase and a decrease in beak sizes. Of the larger beaks get bigger and the smaller beaks get smaller. So this is kind of neat because what this does, it limits the opportunity for competition. Larger beaks will eat the food that they're good at, and then the smaller beaks eat the food that they're good at. And then one thing I see I missed over here, this is kind of, this one was beak size and this one was beak size. I failed to mention this to you. In birth mass, why do you guys think that the center line here, the average, is chosen for? Let me give you a second on that one. Why is the average size baby chosen more frequently than either a large one or a small one? What's that an indicator of? All right, if any of you came up with the idea that large babies are less prone to survive because they don't get passed through the birth canal, and that small babies are generally premature and less survivability as a result of being less prepared to survive, you're correct. If you said anything else, you're just wrong. The end. Big babies kill the mom, little babies don't survive. Anything in here is what's more likely to survive in birth mass. All right? Good. Now, if we go live, I would ask for questions at this point. So if you want to write them down, email them to me, that's fine. Good. In the case of genetic drift, this is not when natural selection favors a gene, but when random events cause a disruption in allele frequency. Is that the same as evolution causing a change in real frequency? I think you can see both sides of it. It's a yes or no. So in natural selection causing a change in allele frequency, there's a favorable trait and there's a less favorable trait, and we see changes in how often they occur. In genetic drift, a random event disrupts I'm looking for that word in here, so I have to write it. So disrupt, right? Disrupt. It might fit. Yes, it's going to fit. So a disruption of a random nature in allele frequency. Is that evolution? Those of you that are thinking yes or talking to your screen, then yes, it is evolution. So some things happen. Natural disasters, for instance. Rivers running through a mountain range. A flood, natural disaster, fire, maybe something improbable like a viral outbreak, for instance, which only happens every couple of million years, right? Let you process that one. So the founder effect is what happens when the new population ends up misrepresenting the original parent population. I'll come over here and do this. Okay. So in our first circle, this one here, I want you to go ahead and count the number of different phenotypes that you see in the circle. You should have come up with 4 because even though the 2 yellows are yellow, they're not exactly the same. The spots could have something to do with sexual selection and so forth, all right? Now let's do the same thing in the bottom circle. Oh, wish I could roll that back. Yep, those of you at home saying 3, that's my bad. 2 blacks are the same, 2 yellows. So 1, 2, 3. My bad. And then down at the bottom, it's the same thing. Yep, emails all the time, boys. I think I'm on 72 today. All right? Let's see what Evan has to say. Take a little side piece. Evan, I know you're bombarded. Yep, isn't that the case? Apologize for late assignment. I did not see the assignment until this morning. I understand we're all transition. Yes, sir. Hey, guys, watch. This is what you're all going to see. I'm reaching out to you this way. Evan, Evan, you are correct. We are going to see that, boys? And look, take care of your group messages. Talk to each other. Definitely, get GroupMe's or text messages going, whatever app. I'm going to give you a little follow-up at the end of this video so that we can talk about what's going to happen moving forward. But try to minimize the emails as much as possible, especially those that are like okay or some. I presume you've read it if you're communicating with me, but definitely check on Evan's status in a minute. But I wanted y'all to see what basically everybody else is getting via email. I'm not calling anybody stupid yet. All right, so back to our blue circle. Good. So Adam, you should have seen 3, just like the one above. I don't know who said 4 there. Somebody in the back row, maybe. I think it was Womack. Okay. So let's take this out of the play now. I'm going to leave the red 3 and the blue 3. Let's look at the overall phenotype. Yay, email. Yay. Okay. All told, see if I hope y'all can see this. I'm gonna put a star. Let's do the star again. We like the star, especially because it's blue and gold. We're gonna text pen. What does that do? I've never seen that guy before. One of these. Come on, fellas, help me out. Creative pen. Okay. We got the black type, yellow with spots, red. This is like a gold if you can't see it. So that's 6. Usually I lean on y'all to help me out here. I think that covers everybody. Y'all feel like you're playing Blue's Clues? Yeah, that's it. So it looks like 6, right? So while each of these populations covers, back here, there's 3 and there's 3. Each of these new populations is only going to represent 60% of the founding population. That's this guy here, okay? And then when one of these new populations this red 3 here, or this blue 3 here, ends up going to a new location, what happens? So 3 out of 5, not the whole population, not this over here, but this, ends up moving to a new place. Look at the outcome. The populations are different. These two populations, population 1 and population 2, are no longer the same as they used to be. So let's recap this slide. A random change. What could have caused this population to get separated into this and this? Well, anything. If there was a flood and they just happen to be on either side of the pond that was created and they can't get across. And I know ladybugs can fly. It's a bad example, but let's say they get separated and they get separated randomly. They're going to end up in different places. And even if the places are the same, can this population here, this red 3, create a red phenotype like this one? And the answer is no, because it didn't exist. If they had been one continuous population, the reds could have existed anywhere, and the greens, not green, I don't know why I said green, blacks, yellows, golds, they all could have existed. But a random event caused a disruption in frequency, as presented here, 3 out of 5 in both cases, and the outcome is different. So what's the take-home lesson? Random events can affect allele frequency just as natural selection can. In either case, the allele frequency has changed. This one is called genetic drift because genetic drift is that random change. It's drifting away from what was common. And then the founder effect then becomes the effect of a founding population starting the new larger population. The founders are different, therefore what is going to be found in the new area has nothing to do. I didn't intend to be punny, just roll that one back. What we'll see in the new area is the effect of the new founders. Okay. 17 minutes. As I suspected, I was going to say 20, and I thought, oh, I'd make it. It'd be easy. Yeah, right. Okay. I know I said 10 to 15, but gee whiz, I talk a lot. Sorry. I'll be quiet now. Y'all can learn on your own. Didn't work out too well for you, did it? So genetic equilibrium. What do we see? Genetic equilibrium. Genetic equilibrium. Equal genetically. Right there. Population is not changing. No evolution. Can this happen? I actually just looked up at the classroom like I was expecting an answer. If this goes on for a month, I'm going to go nuts. Okay. So there's 5 conditions that can disturb equilibrium. So everything we talk about to this point are things that cause evolution, right? What are things that can cause equilibrium? And the way we're going to learn this list here is that these are factors that can disrupt equilibrium or disturb it. If we wrote them differently, we would say that they're factors that can maintain equilibrium. Okay? So non-random mating is like choosing a mate. And if they're choosing a mate, what might they be choosing on? Choice, right? Preference, survivability, alpha male behavior, anything like that. So non-random mating, meaning mating selectively, chooses for better traits, right? Let's come over here now. I'm going to give you an activity to do when we come back to that slide, okay? So all individuals would not have a chance to generate offspring. What happens by the next generation? Some are more prevalent, some are less. That is a disruption in equilibrium. We're going to call that natural selection, right? So non-random mating is rare. Individuals generally choose. Why a small population is critical to disrupting equilibrium is because small populations may not represent the parent population well. We go back to this slide, right? A population of 4 only represents 60% of the parents. So that could cause a disruption equilibrium. If we want to have a larger population to talk about, that's what we're going to do in our next slide when I pull this full circle, okay? Immigration, organisms coming into the population. Emigration, organisms leaving the population, changes allele frequency, right? If allele frequency changes, is that evolution? The answer is yes, right? So genes leaving, or genes coming in, change allele frequency, that's evolution. This one's simple. Mutation. Mutation occurs as that change allele frequency. The answer is yes. So mutation can disrupt. Remember, these are factors that can disrupt or disturb equilibrium. And then finally, natural selection. If natural selection is occurring, obviously, any phenotype that is selected for is going to be more prevalent in the next generation, therefore affecting allele frequency, right? So let's talk about how to maintain equilibrium. So what will we say for this one here? Non-random mating, we would say what? What would cause or allow, let's say allow equilibrium? It's going to be random. I know what you're thinking. You're thinking this ladybug's a hoe, and that's not the case. Random mating is going to maintain equilibrium. It means every organism has a choice, and while you know that doesn't generally occur, random mating would maintain equilibrium, all right? So these are opposites. What type of population would maintain equilibrium? That's large, because every population or every individual is represented. It's not a small portion of it, it's every individual. No movement. I'm going to erase that one and try that again. No movement. We're just going to call this movement immigration and emigration. Okay? No mutation. Isn't my handwriting glorious on this screen with a stylus? And then natural selection. What is it? No natural selection. Okay? If these 5 occur, we keep equilibrium. If these 5 occur, we disrupt equilibrium, right? So can this happen in the wild? Can this happen? Can that happen? Hope you said maybe for a time. You said maybe for a time, that's good. But what is the easiest thing to consider occurring that could disrupt equilibrium? Probably not an easy answer. What about the changing environment? Is Earth always changing? Yeah, Earth is always changing. So we end up in a situation where if a changing Earth, then we can't avoid natural selection. We can't avoid this. Can't avoid mutation. Sometimes organisms leave, sometimes they come back. Small population, that one's a little bit tougher. Right? Sometimes small populations are always available, right? And they're breeding with each other. And then non-random mating, that one can occur, right? So Hardy-Weinberg equilibrium says that if 5 conditions are met, these 5 right here, equilibrium's disrupted. All 5 at one time is not a necessity. One of these disruptions can disrupt equilibrium, changing allele frequency. Okay? Good. Homework is here. You know what to do. And I want to kind of catch all you guys at once, and those of you that are watching the video. The assignment is going to note that you have these questions to do. All right? No problem. As you're doing this, be sure you may be asking me questions. I'm going to post your study. No, you have your study guide. Somebody email me if you don't have your study guide. Just remember that we're trying to move forward and taking a test here, okay? We have a couple of slides left. I want to be sure you guys are watching the video. If you want to, we're going to do the lab at home. We might be able to make this work out, okay? Now let me address this. If you're not getting the video, I'm putting it in a link on Portal. It says like link. I'm hoping that you guys can click on that. I didn't see that many of you watched the previous video that I posted, so I might, you tell me if I can include that in any better way. We'll figure that out together. I'm gonna post this on Portal as I did for 17.1. It was only like 3 slides, so I hope you got it. What I want you to do is be open, be aware that things are going to change, and just communicate with me. I want you to limit the amount of emails that you do send. Obviously, I want everything to go to the eLocker and Portal. I did send something out in regards to that. So follow the instructions that I did post to all of my students on how to use the good old eLocker. It's picture friendly. Talk to your friends, see how they're managing this. I haven't heard from a few of you yet, but that's going to happen moving forward, okay? Again, I am talking to G period right now. If anybody else sees this video, I'm not talking to you, but it might apply. So especially E period this year. All that being considered, we might be moving to something called WebEx, W-E-B-E-X, and that might give us a live learning environment where you guys can either, I'm not sure, I think you can speak your questions or text them, and then some of you might be able to answer them while I'm talking, and we can kind of have a collaboration. And what we're thinking about doing, I have a meeting today, what we're thinking about doing is doing that live for an hour when class schedule permits. So for example, tomorrow, FGAB from 8 to 12, we'd have a class at 9. And for about an hour, we could collaborate and learn that way. I am at school right now making this video on Tuesday. You guys know I live right around the corner. And as long as I can come here, I think I'm going to be most comfortable doing it this way. And I think there's even video feature we can see each other's face. So we have to be appropriate in doing that, okay? So I hope this works out. I spent 27 minutes of my life making it, and I'm going to put it out there for you to look at. And hopefully, if you don't, well, you wouldn't be able to tell me. I'll ask you guys via email if the link is working, okay? I'm going to shut it down for today. Wash your hands, get outside and do some damn activity. And those activities you've been procrastinating on at the house, once you get those done, okay? I will communicate with you guys soon.